Using facts about how Carnot-Carathéodory distance behaves under lift translation and under dilation map, we show that nothing other than 4 can be the Hausdorff dimension of Heisenberg group H1. This does not quite prove that 4 is actually the Hausdorff dimension of this metric space, and hopefully we can do that in a subsequent lecture. From lift translation, I need to recall this important fact that the derivative of lift translation as a map from R3 to R3 is given by this linear map again in the standard basis of R3. The most important thing here for us will be that the determinant of this matrix is 1 at all points. Now, as happened before, we make good use of the fact that H1 and R3 at the end of the day are the same, and therefore we can talk about the Lebesgue L3 measure. The first lemma says that if you have a measurable subset of R3 and then you apply the left translation map to it, you obtain a new set, and I claim that the measure of that set is equal to the original set. The proof of this follows immediately from the area formula, or maybe you know it under the change of variables formula, or even just use substitution. Whatever name you give this, it claims that if you have a one-to-one map, Lipschitz map from Rn to Rn, it maps every measurable set to a measurable set, and that you can obtain the measure by integrating the absolute value of the Jacobian. In other words, the determinant of the derivative matrix. And in this case, as I said, the determinant of the left translation is equal to 1 at all points. Therefore, you simply integrate 1 over E, and that ends up being equal to measure of E. A quick recall of Hausdorff measure. It comes from first approximating by H alpha deltas, where H alpha delta is the supremum of summation of diameters to power alpha. That's why it's alpha dimensional measure. Over all coverings of the set with sets whose diameters are less than delta. And in all of the following, the distance will always be the Carnot-Carathéodory distance, so diameter will be with respect to this. The next lemma shows that H alpha are all left invariant measures on H1 at every alpha. For any accuracy requirement of epsilon positive, there exists delta positive, and there exists delta covering, that means covering with diameters less than delta of E, such that up to epsilon accuracy, the H alpha of E is summation of diameter of EI to the power alpha summation over I. Okay. Now we want to estimate Hausdorff measure of the translation of E, so we find a covering for that translation. A claim, which is really obvious from the fact that Carnot distance is invariant under left translations. Diameter of left translation, so also fix a point P, so left translation by that point of EI as a set we claim has the same diameter as just EI. Yeah, that's just left invariance of the distances and definition of diameter. I'm not going to go that much into details. Now we see that left translation of E is covered by union of left translations of EI, just set theory So now we have a particular covering of LPE with sets of diameter less than or equal delta. So Hausdorff measure alpha at delta content Hausdorff measure of LPE by definition is less than or equal to, let me actually put it up to these estimates. So up to epsilon error, this will be bounded by diameter of LPEI to the power alpha, but that is exactly summation without the LPs, and that was up to epsilon error bounded by H alpha of E plus epsilon, which we absorbed into this. And since delta is arbitrary, we can do this with every delta. As delta goes to 0, with arbitrarily small delta, we see that H alpha of LP of E is less than or equal to H alpha of E. So this shows that the translation decreases the measure but never increases. Reversing the role shows that H alpha of E is less than or equal to H alpha of left translation by P inverse of LP of E, and again by star, this means H alpha of LP of E. So therefore we have equality for them. Now let's visit the dilation map and see how it behaves with Hausdorff measure. Recall that it multiplies the first two components into R and the last component into R squared, and that it's actually linear map from R3 to R3, therefore its derivative is always equal to itself. And finally, that because it's written this way as a matrix with zeros everywhere else, its determinant is R to the power 4, a fact that we will use in a second. Claim: for every alpha positive, the Hausdorff measure H alpha applied to dilation of any set will be R times the Hausdorff measure of the set. The proof is similar in idea to the previous one. And again, just a sketch, if E is covered by union of EI, then delta R of E is covered by union of delta R of EIs, and very importantly, diameter of delta R E EI for any set basically is R times diameter delta R, just EI. And the last part is because we saw that the distance of PQ, R times that is distance of delta RP and delta RQ. And then diameter is supremum of distance of pairs. Apply to every pair, and we get this. So when you estimate Hausdorff measure delta R of E by summation of diameter of these delta R EI coverings to power alpha, and now I ended up finding the bug in my lemma. So this will be diameter of these things to power alpha, so this will be R to alpha diameter EI to alpha. When you factor out this R to alpha, then that part becomes estimating H alpha of EI. Of course, in the actual proof, you start with for every epsilon, there is a delta small, and such that this summation is basically up to epsilon error equal to H alpha of EI, this summation. and you make it just a bit more rigorous. So therefore I end up fixing this, that this has to be R to alpha. So very important fact about how Hausdorff measure behaves on dilations. From this last lemma, I want to prove a simple corollary, but quite important in the next step. Fix again alpha positive if H alpha of E is infinity for some bounded set in H1, then H alpha of F is infinity for every open set. Basically, this is saying that H alpha will just be infinity everywhere in all locations. The proof of this is that by dilation and left translation, we can have a copy of E inside F. Because it's bounded, we dilate and it just comes very near 0. And once we know it's so small that it can fit into a copy of F, we left translate it inside here, and that becomes it. So E is some set. We dilate it here, and this is copy of F, and then we left translate it to here. Now what has happened is that we know that H alpha of F, of course, because it's a measure, is bigger than H alpha of its subset, so this will be copy of E. But this is H alpha of left translation part doesn't do anything, so this is just equal to that. But that we saw is R times H alpha of E, but that is also infinity because R is positive. Similarly, we can see that if H alpha of E is 0 for some open set, I wonder if this is actually a contrapositive of previous claim, then H alpha of F is equal to 0 for all F. And I'm thinking alpha is strictly positive, so I'm not talking about counting measure, but even then it will be true. So the reason I did these two facts is just to come to this conclusion. If H alpha E is positive and finite for some open set, then H alpha of F is also non-zero, non-infinity for every open set. That means it there's this homogeneity to it. It cannot have a mix of a part where this measure is infinite or a part where it is finite. So if H alpha is not trivial, then it is a Haar measure. Technically, what we now prove is only showing that no number other than 4, no positive number other than 4 can possibly be the Hausdorff dimension of the Heisenberg group. The reason I'm not too optimistic here is that our method do not prove that for any open set, say the unit ball, that this is positive and finite. My method, what I do now, is not proving this. All it's proving is exactly what is stated here, that at dimension other than 4, H alpha is trivial, meaning either 0 on all open sets or plus infinity on all open sets. Okay, how do I prove this? I'm going to use the dilation map. We saw in the previous proof that for every set in the Heisenberg group, Hausdorff measure of dilation of E is equal to r to the alpha Hausdorff measure of E itself. We also saw that if H alpha is non-trivial, then there exists this universal C such that H alpha of any set is C times the Lebesgue measure of that. So when we apply this here, we see that, well, H alpha will be the Lebesgue 3 measure of delta R of E, will be R to the alpha Lebesgue measure of E. Because C cancels from both sides. However, L3 of delta R of any set E, again delta R is a bijective Lipschitz map, so measure of image of that will be integrate the determinant of the derivative of delta R, absolute value, dl3 of x over the original set E. But this is r to the 4 regardless of the point x, and that becomes 1e dl3 of x, and that becomes r to the 4 Lebesgue measure of E. Now compare the two equalities that we've shown, from which it follows that r to the alpha should be just r to the 4, and because r is positive, that alpha is 4. So what we proved that is that if H alpha is non-trivial, then alpha should be 4. As I mentioned, I'm not sure if this is actually a proof that H4 is indeed non-trivial. Yeah, there is a subtlety there. And hopefully I will work around this problem and in a subsequent lecture end up showing that exactly H to the 4 is positive and finite on some open sets. But we have established so many of its properties. We know how it reacts to the dilation. It multiplies by a factor of r to the 4, and we have already established that this is the only reasonable dimension for H1, and that it's a multiple of the Lebesgue measure. So many great things we have shown, yet we have not quite proven why H4 itself is non-trivial. Until then, have a good one, and please put in the comments any questions you have, and most hopefully put forth any method you think we can use to do this just by observations about lift translations and dilation, rather than going to deeper stuff like ball box theorem and stuff like that.